going to talk about wave phenomena, reflection, and interference. And for most of this, what I'm going to be doing is looking at wave pulses. And wave pulses are individual segments of a wave. You could have a continuous wave that looks like a sine wave, or you could have a portion of it. You could send one cycle, or you could send a pulse, which is just half of a wave there, one half of a wavelength there. That's okay. They're parts of a wave. And so I'm going to send this pulse over, and I'm going to say that this end of, let's talk about a wire or a spring or a rope or whatever, is connected to the wall there. Well, this is a snapshot. This is what it looks like at one moment of time. Okay? An instant later, maybe it looks like this. An instant after that, maybe it looks like that. An instant after that, maybe it looks like that. Okay? Well, when it finally gets over here, keeps moving, that energy keeps moving. Remember, the particles are just moving back and forth because it's a transverse wave. But when it gets over here, right at the end there, this is going to pull up on here, and Newton's third law means this will pull down on that rope. Okay, so it pulls it down, and what ends up happening is pulling it down. It goes past equilibrium and down there. So the wave comes in. I'll show it as a dashed line. The wave that was coming in like this goes out, flipped over. And again, it's a consequence of Newton's third law. It's a consequence of this anchor pulling back on the thing that's trying to pull it up. So when we have this kind of situation, we can just see reflection makes it go backward. If, by the way, if we make this loose, so this is for a fixed boundary. If we make it loose, we have like a ring there, right? Then a wave that comes in like this, and I'll just draw, this pulse goes in like this, it comes out in the other direction the same way. So that's one thing that happens. And remember, this is energy that's transferring. Pardon me. So the energy transfers over here and then bounces back over there, but the shape of the pulse remains the same, non-inverted. Fixed, loose, unfixed. Okay? So this coming over here, flipping and going back the other way is a characteristic of a fixed boundary for a transverse wave. Now, another thing about this is energy is going through. So if you actually sent a pulse like this, and let's say it's to a loose boundary. Okay, so you've got a pulse coming here, and it would come over, and it would come back the other way, non-inverted. Okay, well, so this will be wave 1. Here's wave 2. I send another pulse. So what I did is I stood over here and I went boom, boom. Okay, and the first pulse goes over there and reflects, and meanwhile I've sent another pulse. So these two pulses are going to hit each other. What's going to happen there? And that's called interference. And interference can be a tiny bit confusing, and it can be very complex just because of the amount of stuff that can be happening. This is changing. So these two pulses are moving towards each other. So 2 moves a little bit, an instant later, and 1 has moved a little bit that way, and they're about to hit. Okay, so there's 1, there's 2. 2 is still going to the right, 1 still going to the left. Interference is when they try to occupy the same space at the same time. So what I'm going to do is I'm going to switch colors here. Actually, I'm just going to add colors here. I'm going to make 1 red. Okay, 1. So let's see what happens after this moves 1 a little bit over this way. Okay, so 1 moves here. Okay, if 1 were the only wave on there, it would look like that. I want to make sure I draw it kind of similar to how I drew it before. And 2 has moved over. So let's see, 1, they're going the same velocity. So let me just, so 2's now, if 2 were the only wave, it would look like that. The string would look like So in interference, we're trying to find out what shape would the spring actually take, or the string, or the rope, or whatever it happens to be. And to check that out, we use a thing called superposition. Superposition. Notice, by the way, when these two things come, they're both trying, the energy is trying to occupy that same space at the same time. It's not really perfect to say it that way, but if we look here, all the way along here, nothing is trying to happen, right? Neither wave pulse 1 or wave pulse 2 are trying to move these particles. Similarly over here. Now what happens in the middle is kind of neat, because 1 is trying to pull the rope up. Let's just take this spot right here. 1 is trying to pull the rope up this far above equilibrium. 2 is trying to pull it this far above equilibrium. Well, those two things contribute together, and that's what superposition means. Superimposing, putting things on top of each other. So the resultant is adding that displacement and that displacement. Put it up there. It would end up being that high. So they add together. Okay? Now, if we add point by point, if I go here and I add 1, wave 1 isn't there, right? So it's not trying to make the thing move in any way. 2 is trying to move it that far. 0 plus this amount means the rope or string or wire would be there. Okay? And then I'm going to move over here. I'm going to say, how about at this spot? Well, once again, 1 doesn't have any energy trying to make it displace in that direction. 2 does. So we add 0, 1's contribution, and 2, and it's there. So it's only when it overlaps that it becomes complicated. If they don't overlap, like here, right? Wave 2 isn't trying to do anything. So this will just basically follow whatever wave 1 is doing there. Same here, up to the point where they overlap. It looks like that. Because in each of those zones, one of the waves is not contributing energy to that displacement. But when they overlap, now we've got to be really careful. Okay, now we've got to say, okay, how about right there? Right there, this displacement is this much from 1. The displacement here from 2 is that much. We add them together, then we get something up here. And if I do this point by point really carefully, what I'll find is something like that. In this range where they overlap, they're both pulling in the same direction. And if we add together the displacements, so in other words, we say, at each point, what is the displacement if only 1 were there? What is the displacement if only 2 were there? Let's add those two displacements together. And we get this interference. Superposition is the process. Add the displacements. That's superposition. Now, when they add together to make a bigger one, in other words, if the displacements are in the same direction, they call it constructive. If they make a smaller, they're in opposite directions, in other words, that's destructive. Notice it's arbitrary what I call positive and negative. So if these two pulses were both on the other side, they would add together to make a bigger negative displacement. That's still constructive. Okay? Let me show you destructive. And this time, let me do it with square waves. Okay? So let's say that here's wave 1 going this way, and it's a square wave. It's going in that direction. Here's wave 1. And here comes wave 2. It's going in the other direction. So wave 2, it's going in that direction. Now, I mean, the rope can only be one place. Right now, they're not overlapped. That's what the rope would look like, or the spring, or the whatever it is. It would look like that. Now, what happens later when they're trying to overlap? And let me draw them. Okay, so I'm going to say here, this one is like this. There's 1. and I'm going to say 2 partly overlaps with it. Like that. So there's 2. Well, let's get our superposition thinking caps on. Here, no displacement. Neither wave pulse is trying to make the string move this way or that way. So no displacement. In here, any point I pick in here, there or there or there, the total displacement would be 0 from the green one and this amount from the red one. So 0 plus this ends up being this. So it ends up following, basically tracing the same position that pulse 1 had. Same thing over here, 0 plus this ends up being this. And we don't know what's going on at the vertical point. Square waves are never perfectly square. They're usually a little tilted. But, okay, so I don't really care about this. I'll even make it a dotted line there. Now here, we've got remember the equilibrium's down here, displacement of 1, if 1 were the only energy on there, and the displacement from 2, if 2 are the only energy on there, they add together, so it makes this kind of shape. Okay? That's the basic concept. Now let's do, I want to show you destructive. Destructive, okay? So now, let me say, okay, here comes 2. 2's like this. But 1's on the other side. Let's say 1 goes this way, going that way, okay? So we have, and again, I'm just going to pick an instant when they overlap, 1. Okay. So again, here's the equilibrium line. Anywhere in here, they're both at 0, so the resultant will be at 0. Here, the resultant would be at 0. Here, 0 plus this is just this. Here, 0, I didn't draw the green there, but 0 for wave 2. Wave 2 is not trying to make a displacement at all, plus this ends up being this. Now, what happens in the middle? Look at this. We've got anywhere in here, we've got a positive displacement from 2. We've got a negative displacement. This minus this ends up being that, right in the middle. It's at equilibrium. They cancel each other out. So the black line indicates where the rope would be. That is what, excuse me, that's what destructive interference does. So what you want to be able to do is, if we had a standard kind of question might be, if we had a grid here and it moves 1 unit per time unit, 1 block per time unit, you could visualize where it would be 1 second later, a second after that, a second after that, and see what that waveform would look like.